Okay, so we're talking about electricity here. We talked about batteries and lightning and the flow of electrical current. Electrical current is the flow of electric charge, and that's going to be electrons. The electrons are flowing through a wire, or it could be ions through a solution. Charged particles that are moving. Oops. Redox reactions can generate electrical current because in these reactions we have an oxidation and a reduction. We have something losing electrons and something gaining electrons. So if we look at this example, zinc metal plus copper ions, those will react and form aqueous zinc ions and solid copper metal. And the reason is that zinc has a greater tendency to lose electrons than copper does. And so the zinc atom will transfer 2 electrons to the copper ion, and then we have a zinc ion and a copper atom. The zinc atom becomes a dissolved zinc ion. The copper is deposited on the zinc as solid copper. And we did look at reactions like this a little bit in 1A. We talked about an activity series of metals. Now we're interested in more about what the electrons are doing. But this is what happens if you put a zinc strip in a solution of copper sulfate ions. They will react. The zinc atoms will give electrons to the copper ions. So the copper ions become copper atoms. The zinc atoms become zinc ions. And so we see this black stuff, and that is copper depositing on the zinc strip, and we can see the color fading. It's not blue anymore. The blue is from the copper ions, and so the copper ions are coming out of the solution. Zinc ions in solution are colorless, so that we don't notice those. So this is a spontaneous redox reaction. Well, if we separate the zinc atoms and the copper ions, they're still going to want to transfer electrons, but we can force them to do it through a wire, generating an electrical current. So an electrochemical cell is a device in which we have a chemical reaction that's either producing electric current or is being carried out by an electrical current. So there are 2 different types of electrochemical cells. Voltaic cells, also known as galvanic cells. These will produce electric current. They're spontaneous reactions. And then we have electrolytic cells. These consume electrical current to drive a non-spontaneous chemical reaction. You can take a non-spontaneous chemical redox reaction, and by forcing electric current into it, you can make the reaction happen, although it wouldn't happen spontaneously on its own. So here, looking again at the zinc and the copper. So this is an illustration of an electrochemical cell. So over here in this beaker, we have zinc ions in solution, and we have a zinc metal electrode. On the right side, we have copper ions in solution and a copper metal electrode. We have a salt bridge here. We'll talk about that later. The zinc ions are pretty happy about losing electrons, giving those electrons to the copper. Here, they're not in direct contact with each other, and so what will happen is those electrons will travel through the wire, through the light bulb, over to the copper over here, where the electrons contact with the copper ions in solution and reduce the copper ions. So the strips of metal are called electrodes. So we've got 2 electrodes, and we have 2 half cells. 2 half cells make a single cell. In each half cell, we have a half reaction occurring. Zinc has a greater tendency to ionize, so its equilibrium lies further to the right. So if we look at the equilibrium here, zinc is in equilibrium with zinc ion and 2 electrons. Copper in equilibrium with copper ion and 2 electrons. So zinc, it has a larger tendency to ionize, so its equilibrium lies further to the right, and copper lies further to the left. So this electrode over here is going to be negative relative to the copper electrode, because there's extra electrons here that are trying to go somewhere. If they're connected by a wire, that gives a place for the electrons to travel. The electrons that are being lost by the zinc will travel through the wire to the copper ions, where they can be gained by the copper. The zinc equilibrium, then, if we lose these electrons, it continues to shift, right? It'll just keep going. And so those electrons go away, it shifts, more zinc dissolves, and more electrons are formed, and the electrons can go over there. And here, electrons come in, combine with copper ions to form solid copper, and as more electrons come in, this reaction continues to go to the left. So we have an oxidation occurring and a reduction. So here's our oxidation, the zinc is losing electrons, the reduction, copper ions are gaining electrons. So that electrical current flow of charged particles is analogous to flowing water. And it's helpful to think of it this way because we're familiar with water and how water behaves, and we can't really see electricity. So the rate of electrons flowing is like the rate of water moving. If you look in the Fresno Bee, you can get the rate of water being released from Pine Flat Dam. Right? They can measure that. So an ampere, abbreviated capital A, is a unit of electrical current. Tells us how fast the electrons are moving, and it's often referred to as an amp. Not an amplifier like you'd hook up to a guitar, but an amp. A coulomb is a unit of electrical charge. So we're accustomed to thinking of electrons as being -1, but that's a relative charge. What actually is their charge? Well, charge is measured in coulombs. So an amp, a rate of electrical current, rate of electrons flowing, is 1 coulomb per second. So it's a specific amount of electrical charge per second. And so 1 coulomb is 6.242 times 10 to the 18th electrons. And so when we talk about 1 amp of current, we're talking about this many electrons moving through a position per second. Now, water current is driven by a difference in gravitational potential energy. Why does water flow down the river? Because the bottom of the river is lower in altitude than the top, right? In a lake, the water just sits there, right? It doesn't flow back and forth or anything because it's reached an equilibrium, it's all level, there's nowhere for it to go. But in a river, the water flows down, right? So electrical current is also driven by a potential difference, but it's not a gravitational potential, it's a potential difference. It's a measure of the difference in potential energy per unit of charge. So we have another unit for this, it's the volt, a unit of potential difference. A volt is 1 joule per coulomb. So the difference in potential energy is 1 joule for every coulomb, if we're talking about 1 volt. If we have a large potential difference, then we have a large difference in charge between the two electrodes and a strong tendency for electrons to flow. This is like a steeply descending stream bed. So here, if you have like a mountain stream where the drop in elevation is very steep, that water is flowing very fast, right? Whereas out in the plains, if there's very little difference in elevation, then the water will be moving more slowly. So the electrons are moving in response to that potential difference. Again, if there's a large potential difference here, the electrons flow quickly, and if there's a small difference, they will not flow as strongly. So what we talk about as the electromotive force, or EMF for short, that's another term that describes potential difference. It's the force that results in the motion of electrons. Any questions yet? I see at least one person on video, so I know at least I'm talking to one person. Thank you. Okay, so if we're looking at that electrochemical cell, we can talk about the cell potential, which is indicated as E cell, or we sometimes call the cell EMF. That's the potential difference between the two electrodes in that voltaic cell. That cell potential depends on the relative tendencies of reactants to undergo oxidation and reduction. We get a high positive cell potential when we have a substance with a high tendency to oxidation being paired with a substance with a high tendency towards reduction. The cell potential is also going to depend somewhat on the concentrations of the solutions and the temperature, and we'll get into that later. The standard cell potential, so E cell with the degree sign up here, that degree sign always stands for standard. That's when we have things occurring under standard conditions, and here standard conditions are described as concentrations of 1 mole per liter, or if there are gases involved, the gas has a pressure of 1 atmosphere. And of course, if you have solids or liquids, they would be pure. So let's pause here and see if we're understanding things. Which statement best captures the difference between volt and amps? The volt is a unit that quantifies the difference in electrical potential energy, and the amp is a unit that quantifies the flow of electrical energy, or electric current. Or the amp is a unit that quantifies the difference in electrical potential energy, and the volt is a unit that quantifies the flow of electrical current. Sometimes all these words are like, whoa, I'm drowning in words. These two statements are opposite of each other. And then the third one is the volt and the amp are two different units used to measure the same thing. They both measure flow of electrical current. Anybody want to give that a try? Yep, it's A. The volt measures difference in potential energy, and the amp measures flow of electrical current. We can go back to this slide. An amp is a unit of electrical current. The volt is a unit of potential difference. So that voltaic cell that we were talking about, we had zinc metal and copper ions, and the zinc was giving electrons to the copper, forming zinc ions and solid copper. And the standard cell potential for this is positive 1.10 volts. If instead of zinc we put nickel in there, the cell potential is going to be lower because nickel has a lower tendency to be oxidized than zinc does. So now the standard cell potential is only positive 0.62 volts. Both of these are positive, which indicates that the reaction is spontaneous in the forward direction. If we get a negative cell potential, that means that the forward reaction is not spontaneous. So this is a slide that I made just to kind of help us remember these terms. because electrochemistry was actually the thing I worked on in graduate school, and I really love electrochemistry. But some of the terms are super confusing because there's all these pairs of things that are opposite. Oxidation, reduction, anode, cathode, cation, anion. I mean, it's just all these different things. So we need to be able to keep these straight. Oxidation occurs at the anode. One thing that can help you remember that is both of those words start with vowels. Reduction occurs at the cathode. You can think about a red cat. Reduction, cathode. Those are both consonants. The anode is more negatively charged. Anions are negative. The cathode is more positively charged. Cations are positive. Right? I almost got a picture in there, but I didn't. So electrons are going to flow from the anode to the cathode. The anode is more negative. The electrons are negative. Negative electrons are repelled by this negative anode. So the electrons are repelled by the negative anode. They are attracted to the positive cathode. So the electricity always flows from the anode to the cathode. Well, there's a little more to this. If we have electrons flowing from the anode to the cathode, that would eventually cause a buildup of charge in the solutions because we've got all these electrons going to the cathode, and so we're going to get an excess of electrons over there and an excess, I guess, of positive charge on the other side. And then things are going to stop. So to compensate for that, we use something called a salt bridge. And this allows counter ions to flow between the two half cells without letting the solutions mix. And so typically this is an inverted U-shaped tube containing a strong electrolyte that will connect the two half cells. So we have this strong electrolyte, sometimes it's sort of a gelatinous material, that will allow negative cations, that'd be great, negative ions to move from the cathode half cell through the salt bridge back to the other side. And so that neutralizes the accumulation of positive at the anode. Positive ions can flow to neutralize negative charge at the cathode. So here's our Voltaic cell again, and now we're going to focus more on this salt bridge. So here, this one's got a glass wool plug to keep the solution in there, but the ions can go through that. So electrons are moving from the zinc anode to the copper cathode. And in solution here, we're making a lot of positive ions. I'm sorry, no, we're using up positive ions. Electrons are coming in, we're using up positive ions. Over here, we're generating positive ions. So we're getting a buildup of positive charge over here. So in here we have potassium nitrate. The potassium ions will come over here to take the place of the positives that got changed, and the negative nitrate ions will come over here to balance the charge with the zinc ions that are being created. So electrons are flowing through the wire, and we also have charges moving through the salt bridge, but they're actually ions, they're not electrons. Any questions? So here's a question. In a voltaic cell, which direction do the electrons flow? From high potential energy to low potential energy? From the cathode to the anode? Or from lower potential energy to higher potential energy? Yep, it's A. Just like water going down a hill, or a ball rolling down a hill goes from high potential energy to lower potential energy, that's the same thing that happens in the voltaic cell. And we can use this. There's two beakers, and there's a little bridge here, a connection, This has higher potential energy, and this has lower potential energy because the level of the liquid is lower. And so we know from practical experience that what's going to happen is the water's going to flow through this tube over here until their levels are the same. It's a similar idea with electrons. They're going from the high potential energy to the low potential energy. So electrochemical cells, we often need to specify what's going on in them, and we don't always want to draw pictures. So this is a cell diagram, and it's sometimes called line notation. So what we've got here is we have the anode on the left, oxidation, and so we've got reduction on the right. And that's just like the electric current. It's going from the anode to the cathode. So just like we read from left to right, we're going to write this out in the same way. In this half cell, we had solid zinc as the electrode and zinc ions in the solution. These are different phases, one's solid, one's aqueous, and so those are separated by one vertical line. Between the two half cells is the salt bridge, and that's represented by two vertical lines. Over here on the right side, we've got solid copper as the electrode and copper ions. And again, those are different phases, so those are separated with a line. If we have multiple species that are in the same phase, they'd be separated by commas instead of lines. Sometimes all the principal species in the half reaction are aqueous. There isn't a solid. So then what we use is an inert metal such as platinum. The platinum is not going to react with anything, but it's going to allow the electrons to get where they need to go. So here's an example. I kind of think we actually balanced that equation earlier. So what we want to do here is write out the two half reactions that are occurring here. So oxidation and reduction. Oxidation is loss of electrons, reduction is gain of electrons. So we can look here at the iron. The iron is going from a neutral atom to a positive ion. It does that by losing electrons. So that's going to be my oxidation. So I've got 5 iron atoms. And on this other side, I'm going to have 5 iron ions. And this is a little bit like doing the half reaction method, except it's already balanced, so we don't have to do as much. Here we have mass balance, but we need charge balance, and so we're going to have 10 electrons over here. And then the reduction, I didn't put the hydrogens or the water in here because I didn't need them. That means they're probably going to be needed in the other one. I've got the permanganate, and I didn't use the hydrogens before, so I'm going to use them now. Oops, I'm going to need a space there. 2 manganese and 8 H2O. So I'm taking everything that I didn't use in the first one, and if I check it out, I'll find that all of the atoms balance just fine. For charge balance, I've got positive 4 over here, and I have 16 minus 2 is 14 over there, and so I need 10 electrons here to get the charge the same on both sides. The number of electrons lost in the oxidation has to equal the number gained in the reduction. And this would be the line notation for this cell. We've got the oxidation is with iron and iron 2 ions, solid and aqueous, so those are separated with a line. There's the salt bridge between the two half cells. Over here, I've got permanganate, and I've got hydrogen ions, and I've got manganese ions. Those are all aqueous, and so instead of putting lines between them, we're going to put commas. And there has to be a solid electrode, and none of those things are solids. They can't be used as electrodes, so platinum is a typical choice for the electrode. Any questions?
Yeah, could you explain why it's the iron that is the oxidation and not the manganese?
Yeah. So what's happening to the iron is that it's losing electrons. Right? It went from Fe0 to Fe2+. So its oxidation state is going up. That's oxidation. We can also look at how does it go from being a neutral atom to a positive ion. It must lose electrons. Oxidation is loss of electrons.
Right, I get that, but isn't am I just like not looking at this correctly? Isn't the manganese, isn't that lose electrons too because it turns to 2+?
So that's an excellent question. So that's where formal charges help us out. So if we look at the permanganate ion, well, we've got manganese and we've got oxygen. There are 4 oxygens. And we know that between those 5 atoms, their formal charges have to add up to -1. Manganese there is part of a polyatomic ion, so we don't know exactly what its charge would be. And so we're going to go for the oxygen first. And what would oxygen choose if it gets to pick? What charge does oxygen have as an ion? -2, right? So the oxygen is going to be -2. I have 4 of those. So times 4. So I've got a total of -8. And so this total from the oxygens and the manganese has to add up to -1. So the manganese is actually +7. It's +7 over here, and it's +2 over there. So although it's still a cation, it has gained electrons, and it's not obvious.
Perfect, thank you.
Mm-hmm. Any other questions? That's probably why I probably shouldn't skip that first step on those other, but I did. And I don't remember why I put this picture in here again. Oh, because this is a different, this is not the same cell we were looking at before. Here we've got an iron electrode here, and the Fe2+ ions. And so this is the anode, this is losing electrons. They're going to go over to the cathode. Here the cathode is platinum, because we don't have any solid that we could use. And reduction is happening over here. The permanganate ion is being changed into manganese ion. Yeah, the slide numbers are a little different because I updated them and I forgot to upload them to Canvas. So mostly it's just missing those conceptual questions. Most of the content is the same.